Hi, I'm Carl, and I wanted to do a little bit of a video for this forum post. Thought it might be easier than trying to attach a million images to Blackboard. So I wanted to have a look at simulation data and some of the stats and things that we can get out of them. So instead of actually running a simulation, what I've done is downloaded this Python package called PinBody, and it comes with some test data from a test simulation, and they give it to you to run some analysis and stuff on. So thought that would be fun, a bit interesting to do. I don't know how realistic the simulation is, so some of the stats and images and things that come up may not be realistic, but I'd be interested if some classmates want to comment on those aspects of it. So I think that might be quite good to do. So let's have a look. So the first thing we can do is get some general stats about the data in the simulation. So we can see that this one here is using, or has used 1.7 million particles. Most of those, just over 1 million, are dark matter, and we've got a small number of gas and stars in that as well. Next thing we want to do is have a look at what they call halos. So halos are the larger clumps, or the larger denser areas of the simulation that end up coming out at the end. And here we found 1,400 of them. So these could be considered galaxies. The next thing we're going to do is center in on the largest one of those. We're going to convert all the units into physical units, things like kiloparsecs and kilometers per second, so they're a bit easier to work with. And we're going to have a look at some of the large scale structures. So it's converting all the units there for us. And we can have a look at the large scale dark matter structure here. So what we're going to look at is we're going to plot in an image the dark matter, that's the D, contained within 10 megaparsecs of the simulation. So this is the middle 10 megaparsecs. Now the data is only about 10 megaparsecs, so we can't go much larger than that. And this is our structure here. So we can see there are, in some ways, some filaments, I guess. There's larger, denser, clusters. This is one of the largest areas here, which we're going to take a look at in a moment in some more detail. But we can zoom in on any area of this and take a bit of a look. The resolution, again, isn't that great. That's only because it's a small data set. It's not that massive. So we can zoom in on various parts and take a look at what's happening there. So we're now going to find the largest halo, so that was that first one I identified, and we can do some basic stats on this as well. So that's this piece of code here. So we can get the number of particles, the number of dark matter particles, gas and stars, but we can also have a look at the overall mass. So each particle in this data set has a mass assigned to it, as well as its three-dimensional location. And the total mass of this particular halo, or this galaxy, is about 1.6 by 10 to the 12 solar masses. We can see that most of it is made up by dark matter and the gas and stars. So we've been dealing with velocity dispersions and the virial theorem, so I thought it'd be interesting just to do a quick little stat on that for this galaxy. Again, I don't know how realistic that is, but we get the velocity dispersion and we get the mean of that and print that out here. So we've got, I think this is based on the gas particles in this simulation, traveling at, on average, 96 kilometers per second. So the next thing we're going to have a look at some nicer images of this. Let's have a look at what this galaxy actually looks like in a little bit of detail while it's calculating. What we're going to do, each one of those particles again has other data as well as mass and location. It has magnitudes of various color bands. And we're going to plot the I, V and U bands. and we're going to have a look at that side on. So this is our galaxy. So again, we can zoom into certain parts. It's quite red, but there are some blue areas in the tails there along the side. It's not too bad an image. Going to have a look now at the gas density. So just the gas components of that galaxy, which is this G here. We're going to map those in a blue color and have a look at what that looks like. So in that galaxy, this is face on now, so we've turned this on its side, and we can see there's a large density of gas as we approach the center, and that decreases generally as we go further out. Although there are some clumps on the outer edges there as well. We can now have a look at the density side on as well. So we've turned the galaxy on its side, and we can see a similar pattern, denser as we approach the middle, but also that the density is in a line across. So this is more like a spiral or a disk galaxy structure rather than elliptical structure, which would have gas, I would assume, to be much more spherically located, whereas the top and lower areas here are quite light on gas. We can also have a look at temperature. This was an odd looking graph. Somebody may want to delve in and see how realistic this is. Again, we're looking at similar scales, and the darker the red, the hotter the area. So you can see that it's not very hot in the middle there, but there is this band out here that does get quite warm. So I'm not sure how realistic that is. That seems quite odd to me. So if somebody wants to comment on that, I'd be interested to know. We can have a look, although, at the temperature profile, which gives us a much more realistic view, I think. And we see that closer to the center of the galaxy, we are much hotter at 10 to the 6 kelvins, and that decreases gradually as we move further out. We've done some work on rotation profiles, so I thought it'd be interesting to show this one as our last graph. So here what we do, we grab that particular halo we're looking at, and we get the log of all the velocities of that particular, or the particles that are in that particular halo. And we do the same separately for just the gas, the stars, and the dark matter. And we can plot here the circular velocity of those, and this is what we get. Again, I'd be interested if some other classmates wanted to comment on this, on how realistic this looks. Get the total rotation curve is this top blue one, and we see that it's quite fast, in the top, close to the center of the galaxy, and it gradually decreases. Well, there's a big drop, but then it gradually decreases after that. Dark matter is our next line here, which follows the total curve, but doesn't peak in the same way. Stars tend to follow the same shape, although they decline very quickly in velocity. And the gas is basically quite flat throughout, so consistent velocity throughout the galaxy. So again, I'd be curious to have somebody comment on this and let me know how realistic this simulation is and the data that's come out of it. Otherwise, I hope you found this useful, and we'll see you soon. Cheers.